Okay, Dalton's law of partial pressures. I sometimes find that that adjective partial is confusing for people. So let's be clear about Dalton's law here of partial pressures. We're talking about a mixture of gases. And it's very simply that the total pressure of the mixture is really the sum of the pressures of the individual gases in the mixture. So I'm going to use the expression P subscript capital T for P total, and that is now going to be the sum of the pressures of the individual gases in the mixture. And that's the idea of a partial pressure. It's just the pressure of a gas that's in a mixture. So when we use the designation there, let's say we have a mixture of oxygen gas and helium. Then we have the partial pressure of oxygen plus the partial pressure of helium equals the total pressure. Or in general, Dalton's law can be written P1 plus P2, for however many gases are in the mixture. So here's a mixture of two gases. We have the blue gas and the red gas. So let's say that the blue gas is argon and the red gas is helium. The total pressure of the mixture is 102 kilopascals. So we know that from Dalton's law that the total pressure is equal to the sum of those individual pressures. True. Now, what other information do we have here? Well, we have the number of particles if we count the dots as the particles. And so if I count up the blue dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, looks like there's 10 of those and 5 of the helium. So to determine the partial pressure of the argon, well, what percentage of these particles are argon? Well, 10 out of the 15 are argon, right? So I can multiply that by the total pressure in order to determine the partial pressure of argon. So you'll notice here that I counted the particles of argon over the total and multiplied by the total number of particles and multiplied by the total pressure. 3 sig figs here, since these are just counted values, so 3 sig figs, and I went 3 sig figs. Now, in reality, you wouldn't have the number of particles, you'd likely have moles. So if you knew the moles, or even the percent, perhaps they said, 67% of the mixture is argon, in which case you can just change that 67% to a decimal and multiply by the total pressure. So these questions are, vary from being given the individual pressures and just ask for the total. Perhaps you're given the total and one of the individual pressures and asked to find the remaining one. Or perhaps you know something about the percent of the mixture that is a certain gas or the number of particles. Okay, we're looking for the partial pressure of the helium also. Well, if we know that the total is 102, right, then we can subtract the 68, or we could have looked at 33%, 5 out of 15 times 102. And so we come up with 34 kilopascals. So really that's the basic concept right there. Now, how do we apply that in our experimentation? Well, we can collect a gas over pressure. So when collecting a gas over pressure, the experimental setup looks something like this. We have an inverted graduated cylinder that has been filled with water and inverted so that the entire cylinder is full of water. There's no air in here. We'll put that in a sink or a larger container that has water. A reaction occurring in a flask that can be stoppered and have a pipe and a hose attached such that that gas, as it's produced, right, the green bubbles here, let's say this is a piece of magnesium and acid. So hydrogen gas is being produced and it will move through the tube and end up bubbling up into the graduated cylinder. Now, the graduated cylinder that previously was full of water, right, that water is going to come out now. The water will leave, and so it's the displacement of the water in the graduated cylinder by the gas. Then that's how we collect the gas. Of course, this water level is going to start to rise as the water from the cylinder moves out of the cylinder and is replaced by the gas. Because it's a graduated cylinder, we can actually measure the volume in milliliters. Now, later on, if we're using that in a gas calculation, we'll definitely have to convert to liters. However, if we're using some form of the ideal gas law. However, that measures the volume for us. We can use a thermometer to measure the temperature in degrees Celsius and just add 273 to convert to Kelvin. And we can measure the pressure of the atmosphere with a barometer. Now, what's happening inside that graduated cylinder? So let's expand that for a moment and think about that. Okay, so I've shown the inverted graduated cylinder magnified here, and you can see the green dots representing the hydrogen gas that was produced in the reaction. Now, what about the water? Do you think that gas is in the graduated cylinder is just hydrogen gas? Well, think about what happens if you leave an empty glass of water on the counter. Over the course of the day, that volume of water will decrease, right? What's happened to the water? Correct, it has evaporated. And so in fact, what we really have when we're collecting a gas over water is a mixture. There's definitely a mixture of the gas that we are trying to study, I'll call that the dry gas, and water vapor. The total pressure of that mixture is going to be the atmospheric pressure in the room. And so using Dalton's law, the total pressure of the mixture, or that atmospheric pressure, will be the pressure of the dry gas plus the pressure of the water vapor. Now this is a value that you can look up in a table. So we have that information on our test reference page. You could also find it in your textbook or any reference source online. And as long as you know the temperature of the water at that point with a thermometer, you'll be able to determine the partial pressure of the water vapor. And so you'll see that I transferred that equation up here where I'm listing the given from my experimental setup, and that atmospheric pressure, the total pressure, is the sum of the pressure of the hydrogen gas and the water vapor. So I'll look this one up in a table. We can measure the atmospheric pressure in the room with a barometer, and so ultimately isolate the partial pressure of the hydrogen. And this process here, so subtracting the water vapor pressure from the atmospheric pressure, we call correcting the pressure. So we essentially need to determine the pressure of only the green particles in here, not the blue. So the green being the hydrogen gas, and that's the gas that was actually produced in the experiment, and that's the gas that we want to do our calculation with, whatever the case may be. So with the concept of collecting a gas over pressure, you should understand that in fact we collect a mixture because the water will be evaporating. The mixture is truly a wet gas, right? So the idea is that this is thought of as a wet gas because it's the gas that we're interested in the experiment and the water vapor. And so we need to make sure, because of Dalton's law of partial pressures, that we correct the pressure by subtracting the water vapor pressure, which again is a value that can be looked up easily. Okay, that's it for Dalton's law of partial pressures.